The fourth question says, three particles A, B and C are situated at the vertices of an equilateral triangle ABC of side D at time t is equal to 0. Each of the particles moves with constant speed v. A always has its velocity along AB, B along BC and C along CA. At what time will the particles meet each other? Now, this figure here shows how these particles would start moving initially. C always would chase A would chase B, and B would chase C. You may easily get tricked into believing that these particles would then keep traveling along the edges of or the sides of this triangle, and they would keep circulating just like that. But that is wrong. Since these particles are moving, when A moves towards B, the point A is getting shifted, and C would have to shift its motion from its initial path slightly away from it to chase A. And A would do the same to chase B, and B would do the same to chase C. So they would move spirally inward, and they would meet at the center of this equilateral triangle because everything is symmetric here. It's initially an equilateral triangle, and these particles are moving with the same exact velocity. We'll see how these particles are moving with a better figure, which is here. And you can see that each of these particles follow a trajectory that is marked with a dotted line here, and they would all tend to move towards the center of the equilateral triangle. And the imaginary triangle that connects these three particles will remain intact even when they rearrange their positions. And that is because everything is symmetric here. The velocities are equal, and it is initially an equilateral triangle. So they would converge spirally inward, and they would reach the center of this triangle. Now, how do we find the time when these particles would collide? Let's look at one single line here, a pair of particles here, that is C and A. Any one would do, any pair would be sufficient, but we'll choose C and A now. So you have the particle C here and the particle A here. C will be always moving along CA or towards A with a velocity v. And A would always be moving towards B with again the same velocity v. And this angle here would be 60 degrees because it's an equilateral triangle. The equilateral triangle is maintained throughout. And the initial separation, the relative separation between them is d initially when they begin to move. And finally, when they collide, the separation would become 0. So the relative displacement in the process is d. Now, what is the relative velocity here? This is v. That is the velocity that the particle C has towards A is v. And if I take the component of the velocity of A along this line here, along CA, I can say that that component would be this way here, and that will be equal to v cos 60, and v cos 60 will be v into 1 by 2, that is v by 2. So you have along the same line, you have v forward and v by 2 backward. The relative velocity here would be v minus v by 2 because it's in the opposite direction, and that will be v plus v by 2, that will be 3v by 2. Now, the relative velocity along the line CA is 3v by 2. The relative separation initially was d, and the relative displacement is d itself because finally they meet together. So you know the relative displacement and the relative velocity. So the time will be equal to relative displacement by relative velocity, displacement relative by velocity relative, that will be equal to d divided by 3v by 2, and finally the answer would be 2d by 3v. If I rearrange it, t will be equal to 2d by 3v. So that is how we solve it. You can solve similar questions with this method. There are many questions that can be asked in the same pattern. You can have particles at the vertices of a square, and you can have particles at the vertices of a hexagon or a pentagon. any irregular shape can be solved, or any problem with a regular shape and the particles at the vertices can be solved using this logic. You take one side separately, and you know that when the particles collide at the center, that side would be relatively covered. So relative displacement is already that side, and you can find the relative velocity along that side by drawing it apart and finding the components of velocities here, just like we did it in this case. So that is how you solve such questions.